I'm Associate Professor Benjamin Holcomb from the Centre for Audio Acoustics and Vibration at UTS. I'm here in our acoustics lab at our Tech Lab facility at Botany campus. And this video is to demonstrate some of our unique capability in the country in respect of scanning laser Doppler vibrometry. This device here is a scanning laser Doppler vibrometer. It makes use of an infrared laser as a measurement laser, and it also has a pulsed diode laser, a green laser in there, to allow us to know where the laser beam is pointing. This is a non-contact vibration measurement technique that makes use of the Doppler effect to determine the velocity of the surface, the vibration of the surface, for which the Doppler shift on the laser beam is directly proportional. This device has a pair of orthogonal mirrors inside that are controlled by our computer system. That allows the laser beam to be repositioned sequentially across different locations on the axisymmetric disc or on any of our sample structures that we might be interested in making measurements from. These axisymmetric structures are quite interesting. We are able to predict very nicely the vibration frequencies of these kinds of structures. The structure is vibrating, which we can hear because of the fact that I'm using a Qsources lightweight shaker, a mini-inertial shaker attached to the backside of the disc. And the combination of these two non-contact vibration measurement technique with the laser vibrometer and essentially very light mass loadings, almost zero mass loading for them from the mini-inertial shaker, and zero stiffness loading to the disc means that we're able to very precisely characterize the vibration behavior of these kinds of structures. I'm talking about resonant frequencies and mode shapes. And by collecting a series of frequency response functions which describe the response of the structure for a given excitation by the shaker, we're able to process those data in the software system and produce these natural frequencies and mode shapes for these kinds of structures. This is a chirp that's being used to excite the structure. We're sweeping through a wide frequency range from 100 Hertz all the way up to 10 kilohertz. If we come around and have a look at the software now, I can describe what's happening here. This is the software solution that we're using that's delivered by Polytec with the scanning laser vibrometer. I've set this measurement up with a series of data points. I've got 155 discrete points around the axisymmetric ring here, and you can see that some of those points have been measured. Some of them are optimal, they're colored in teal. Some of them are valid, they're colored in green. Others are unmeasured, currently they're still in blue. The software will drive the vibrometer around the structure until it's made measurements at all of the blue points, ideally turning them to teal. In the case of the green points, where they're for the time being valid only, it will readdress those points, adjust some of the settings, try to improve the quality of the signal that's been collected to get them to go from optimal, from green, from valid to optimal, i.e. to teal. These two curves here are showing the time domain measurements. So the lightweight inertial shaker has an integrated force transducer within it, and that's the time domain signal here that's being captured. As you can see, we're largely trying to produce a constant level forcing function to excite the structure. The response of the structure, however, is this signal here, and what you can see very nicely encoded in here from low frequencies up to high frequencies at this end. As the excitation passes through a resonant frequency, we get lots of vibration response. So you can already see in this signal something about the characteristics of the structure under test. But we have to do more than that to be able to really turn this information into something very useful. And that is the next screen here. So this is a frequency response function. This function is produced by dividing the response of the structure in velocity by the excitation that we're subjecting the structure to in newtons. And the peaks in the spectrum here, which you can see, are all of the resonant frequencies of the structure. So there's a fundamental frequency here at 342.6 hertz, and then subsequently higher order frequency responses. As we increase in frequency from 0 hertz to 10 kilohertz, there are further and further resonances. For this kind of a continuous structure, effectively we have an infinite number of resonant frequencies, but we constrain ourselves to investigating the dynamics of the structure over this 0 to 10 kilohertz range. As we increase in frequency, the complexity of the mode shapes becomes more spatially. There are more complex shapes, and I'll show some of those shapes in post-processing subsequently. The other curve that I have here is a coherence function. The coherence function gives me an indication of the signal to noise ratio of the measurements, and so this is taking into account the signal to noise ratio of both the vibrometer measurement and the excitation signal measurement, and we're aiming for a value of nominally 1. And as you can see, with this combination of lightweight shaker and laser vibrometer, we get a very nice looking coherence measurement, except for at the anti-resonances, and we only get a coherence measurement after we've done the second averages. So once per 3 averages, you will notice that this coherence function is essentially meaningless temporarily. Actually, it's just zoomed into 1, and then we get some dips in the signal at our anti-resonances, but we don't really care about that, because what we're interested in is making sure that we have excellent signal to noise ratio at the resonant frequency. So wherever I have a resonance, I should get very nice looking coherence. At different locations on the structure, I have different amounts of response per frequency. So there's also something encoded essentially within the coherence function that's a function of where exactly we are on the disk. The coherence function is used as a measurement of the quality of the measurement that we're making. So we keep an eye on that while we're collecting our FRFs, and then we come over to do some post-processing. So we'll just move over to this monitor and have a look here at a measurement campaign that we did earlier. And so here are the kinds of signals that we expect to see. Here is the sum FRF. So there's our fundamental frequency, which I mentioned at 342.6 hertz. There is higher frequencies and so on. So we select those frequencies with bands, which helps the software do the processing. We can then process those data, and we can animate immediately on the display those mode shapes at those various frequencies that appear in this list here. So there's a pair of axial modes, as we refer to them, at the first and second resonant frequency. And here now you can see this increasing spatial complexity of these modes. I'm just going to skip one and go to the next axial mode because I know where it is. Higher order axial mode and so on. So we get increasing numbers of modal diameters as we increase in frequency. There are some other modes that we can measure here, and these are what we refer to as torsional modes. So in this case, the ring is essentially rotating torsionally about its neutral axis, and that's the first m=0 torsional mode. There is no nodal diameter. The second torsional mode is here with 1 nodal diameter, and as I increase, I'll find the third torsional mode, fourth torsional mode. That was the 5th torsional mode, and so on. Because we're measuring out of plane here with this measurement technique, we're sensitive to velocity in the direction of the laser beam. We're more sensitive to these types of modes than we are to other types of modes, which might be in plane in terms of the vibration. We would also need to excite the structure in plane to be able to excite those modes as well. They're much higher in frequency because the structure is much stiffer in plane than it is out of plane in this particular case. That concludes my video from our acoustics labs on scanning laser Doppler vibrometry. I've been Ben Holcomb, I'm Associate Professor at UTS. Thank you for watching, and if you're interested, look at my other videos. I have a sister video to this on continuous scanning laser vibrometry and many other videos on my YouTube channel, so please have a look, like and subscribe. Thank you very much.